In this video, I'm going to explain how to apply Bayes' theorem. So in Lane's book, this is referred to as base rates. And at the end of chapter 5, you actually have a couple of problems where you have to use Bayes' theorem. Okay, so when do we want to use Bayes' theorem? Before watching this video, you should have looked at basic probability. So the beginning of Lane's chapter. If you haven't done that, you should look at that before you try and follow along what we're doing in this video. Otherwise, you're going to quickly get lost. Okay, so Bayes' theorem is used when we have some new information that affects a current estimate of probability. Now, let me show you some examples of that, and it'll make a little more sense. All right. And so it's key to understanding something called conditional probability. Now, the way this is usually written, you might say something like, what is the probability of an event occurring given we have this other event or this other factor affecting probability? And it can also be written this way, probability of A and then this line with a B. This is read just as I said that. So it's the probability of A given B. Okay. All right, so here's an example explaining how this works. And with this sort of thing, this could be very important as we're watching COVID-19 spreading all over the country right now. Understanding how Bayes' theorem is useful can be useful for understanding a lot of these tests that are coming out there. Okay, so we won't talk about Bayes' theorem, and we won't talk about COVID-19, but we'll talk about cancer, for example. Let's say that you go in, you get a mammogram, all right, and you come back with like a positive result. How likely is it that you actually have the cancer? Well, we need a little bit of information. We need to know, first of all, how common is this cancer? And then we need to know how effective the test is. All right. So let's say you go and have a mammogram done and you get a positive test result. What is the probability? Now, some information we've got is summarized in this table up here. So let's see what we have. First, this cancer is rare. Let's say it's only in 1% of the population. That means out of all the people out there, only 1% of them have this type of cancer. 99% of them don't. Okay? Now how about the test? How good is the test? Well, if you give somebody who has cancer a test, it's going to give you a positive result 80% of the time. On the other hand, if you give somebody who doesn't have cancer this test, it is going to be wrong 9.6% of the time. So you could sort of think of this as a false positive. This is a true positive. All right? Notice these two things are not additive, but these two are. I mean, if you think about this, it's completely logical. Either people have cancer or they don't. All right? But these two things are independent of one another in a way, I suppose. Okay, on the other hand, if you give somebody this test and they have cancer, it's wrong 20% of the time. It tells you it's negative. Notice those two have to be additive. These also have to be additive. Okay. All right, so what does it mean then if you go get a test? Does it mean you have an 80% chance of having cancer? No, it doesn't. And the reason for that is two things have to be true. You have to, your test was positive, all right, we know that. It has to be right? But you also have to be one of these people who has cancer. So how do we deal with a situation like this? All right. So what a positive test means, let's talk about that. So first of all, we are looking for the probability of a favorable outcome out of all the possible outcomes. All you know is that you have a positive test. So in other words, you could be one of these people who has cancer and has a positive test, but you could also be one of these people, someone who doesn't have cancer but still got a positive test. You see what I mean? Now this is similar to if we roll dice and we want to know how likely it is that a 5 is going to come up. Well, it is a favorable outcome, that's the 5, out of all possible outcomes. There's 6 different outcomes. And that's what we have here. We want to know how likely it is that we have, well, we call it favorable, it's not really favorable, but how likely is it that we have cancer and we got a positive test out of all possible outcomes? In other words, these people plus these people. All right, so to do that, it's just you simply set up a, first of all, you have to figure out what a true positive means, like how likely is that. So for a true positive, to get a true positive, 2 things have to happen. So you have to test positive, there's an 80% chance of that, and you have to be, in the cancer group. So since these 2 things have to be true, the probability of a true positive is the product of the 2 probabilities. So that's the probability of a true positive. All right? All positives, though, so it's the product of these 2 plus the product of those 2. All right? So in other words, you need to add those 2 together. All right? So then the probability that you actually have cancer, that's the favorable outcome over all possible outcomes, you would take the product of those 2 divided by the sum of this product plus that product. Anyway, when you work all that out, and this is in the PowerPoint, so I'll let you go ahead and try it on your own, you should get 7.8%. Okay? As you can see, this is much less than 80%. And, it's interesting. A lot of times patients go into their doctor, and they get this test. If all they know is how accurate the test is when they have the disease, they might draw a very mistaken conclusion. The doctor may say, well, you got a positive result for cancer, and, the test is accurate 80% of the time. Then they think, oh my God, I've almost certainly got cancer, I need to have surgery. Well, not so fast, because you have to take into account how common the cancer is, and you have to know how frequently the tests are, or how frequently you get these false positives. With that information, then you can figure out exactly how likely it is that you have this. So the same thing is happening currently with the spread of COVID-19. Okay. All right, so in this is the same PowerPoint I've loaded onto D2L for you to look at. I'm going to skip down to these other examples here. So the other examples, we've got an example of a weatherman who predicts rain, and we've got an example of an entomologist predicting, how likely a certain beetle is to be a rare beetle. All right? There are many others online. If you want extra practice with this sort of thing, you can just search, for Bayes problems. But you have these to work with. You have a couple more that Lane gives you. So these 2, I would like for you to try and figure them out on your own first. So try to set up a table using that information. Try and set up a table kind of like we did, or kind of like I did here, and see if you can get the answers to these things. And I've actually provided the answers in this PowerPoint here. So the answer to the first one is 0.11, and the answer to the other one is 0.019. Okay, now, so try that on your own first. But in this same video, I'm going to set these up on the board so you can see how to do them. And so you can stop the tape now, see if you can do it on your own. But if you can't, then start the tape and continue. So we'll move over here to the whiteboard so you guys can see what's going on with these. All right, I'm going to have to adjust things a little bit here. Give me just a minute. Now my camera is not sophisticated enough to where I can stop it and start it because it's not a video camera, it's just a regular SLR type camera, I guess. Okay, so hopefully you're going to be able to see what's happening here. Alright, so here's a table that I set up for the weatherman. So we have this prior knowledge. So what we know in this area, it only rains 5 out of 365 days out of the year. That means 360 days out of the year, there's no rain, okay? And then we have some information, some new information about how the weatherman is at predicting rain. So when it's actually going to rain, he predicts rain correctly 90% of the time. On the other hand, he will predict no rain 10% of the time. Now in this example, notice that these two things are additive, but they don't have to be. Remember, this is independent. I've talked about that before. Okay, so here's what we got. Tomorrow, the weatherman says it's going to rain. How likely is it that it will actually rain? Okay, so that's what we have over here. I'm sure you guys can see the formula. Let's see here. Okay, so we have the probability of a favorable outcome divided by all possible outcomes. So a favorable outcome is that it is one of those days that he rains, and he predicts correctly that it's going to rain. All right. So in both of these situations, he's predicted it's raining. That's, so we need the favorable ones. It actually rains over all of the times he predicts. Okay, so the favorable prediction is he's got a 90% chance of being right times the number of days out of the year. Okay, so that is part of our all possible. And then what we have here, these are the times he says it's going to rain, right, 10%, but it doesn't actually rain. Now when you crank through that, you should get 11%. Okay, so now let's take a look at the beetle example. Alright, make sure everybody can see this okay. Alright, so once again we have some prior knowledge. In this beetle, it's very rare. Okay, so out of all these beetles, only 0.1% of them are the rare species. The rest are the common species. So these two things have to add up. I mean, there's only two options. Either it's the rare one or the common one. Okay, only two species involved. So they've got to add to 1. And then they can either have this pattern or they don't have the pattern. And these don't have to be additive, right? Because this common species could have the pattern at any frequency. But we have some new information. The common species has this pattern 5% of the time. The rare species has the pattern 98% of the time. All right? Okay, those two don't have to add up, but what if you needed some of this information about none? Well, you could find that because these would have to. Either the beetle, the rare beetle has it, or it doesn't have the pattern, so that's got to add to 1. All right, we don't actually need that information for this particular question. Okay, so the question is asking, well, we see something with a pattern. So we're in this top row here. It's got a pattern. How likely is it that it's the rare beetle? Okay, well, two things have to be true, right? It's got to have the pattern and it's got to be the rare beetle. All right. But all we know is it's got the pattern, so it could be this as well. So we need a ratio of rare with the pattern. Let me make sure this is visible here. All right, we need a ratio of rare with the pattern divided by all of the beetles with patterns. Okay, so for it to be rare in the pattern, two things have to be true. It has to be in the, the rare beetle, which is like 0.1%, right? And it's got to have the pattern, most of them do, so times 98%. Now we divide that by all the beetles with the pattern. So here we have the rare beetles with the pattern, and here we have the common beetles with the pattern. So in the common beetles, you know, most of the beetles are common. You know, they're 0.999% of the population. And then, but of those, only 5% have the pattern. So two things have to happen to get a common pattern beetle. All right, when you crank through this one, you should get 0.019 as your answer. And with that, we will end the video on Bayesian theorem.